Good morning, everybody. I'll bring more disk drives on Thursday. I see more of you burned out the coils, but that's okay. Good. Something about the assignment. One of the students here raised a good point that when you do the test for demagnetization, you may need to use some voltages or currents which are already getting to be beyond the standard 60 volt, which is considered safe. As you know, in electrical engineering, anything below 60 volt is considered intrinsically safe. You don't need regulations about it. Anything above that, the higher, the more regulations. So some of you may not have access to a power supply which has more voltage, and even if you do, you have to be careful. One way to generate higher voltages, especially if you need them just for a very short time, because otherwise you'll burn out the coil anyway, is to charge up capacitors and use them as a power supply. So if you can find some big electrolytic capacitors, so let's say you connect 3 electrolytic capacitors in series, okay? Now you take your power supply, and let's say you have a power supply which is only 24 volts. So you touch the first capacitor, this is plus, this is minus, and charge it up. Then you touch the second capacitor, charge it up. Then you charge the third capacitor, and now you got 3 times the voltage, right? So if this is 24 volt, you got 72 volt, and so on. And then the nice thing about it is that you don't have to be very quick when you touch the coil, because this will discharge anyway. Matter of fact, you can calculate, okay, how long it will take until it discharges, and so on. Now when you do that, sometimes it's a good idea, when you do tests like this, to put a diode like this. So here is you're going to touch the coil, okay, with a push button or just touching it by hand. Sometimes it's a good thing to put a diode. Now can somebody think why? Pardon? Well, in general, especially with electrolytic, but it's in general in these experiments sometimes it's good to put a diode. So, why did you say if they're electrolytic? Because it's the same reason. So why? But you charge them up always in the right polarity. Okay. Okay, so the answer is very simple. What happens if you discharge a capacitor into a coil? So you must have done this experiment in Physics 101. When you take a coil and a capacitor, what happens?
You need a return path for the inductor's current that goes through the diode.
Not quite, because you can take a capacitor and connect it to a coil with a switch. So when you do that, what will happen? Oscillations, that's the story. So what happens here when you take any capacitor and touch it to a coil, besides a little spark, the current waveform will do like this, okay? And because these are electrolytic capacitors, you are not supposed to give them reverse polarity voltage. The truth is it wouldn't damage them, but you also want to have a controlled experiment. What you want to have is a pulse of current like this, and just to have a controlled experiment, you don't want to have the pulse ringing and so on, because then you're not quite sure what you're testing. So the diode guarantees that after the first oscillation, all the energy is dissipated in the diode, and there's no more oscillations. So A protects the capacitors, B it gives you a much more controlled waveform. So if you ground this end and you connect a scope to see what's going on, you don't need to. For the assignment, you don't need a scope, but for curiosity, if you connect a scope, you'll see that without the diode, depending on how you connect and so on, you get some erratic waveform, typically because of bounce. You get some erratic waveform because sometimes you get bounce, and with the capacitor you also get something not so beautiful because of the contact bounce, but at least it's a single pulse. Okay? So whenever you discharge capacitors, A lot of times you use this setup for magnetizing. That's how you magnetize a magnet. But without the diode, it doesn't work. Because if the polarity reverses and reverses, so this magnetizes it one way, this magnetizes the other way, again one way, again the other way, and at the end, it decays to zero and it leaves it unmagnetized. By the way, that's exactly how a degausser works. The equipment used to demagnetize is exactly like this without the diode. Because what it does, right, it gives you a decaying sine wave which flips the polarity until it reaches zero. Okay? Now you know. So let's move on to the subject which will continue with rotating field motors. So last week I gave you a demo by using a slowed down variable frequency drive to show you exactly how you make a rotating field. And I mentioned that the rotating field you make from two phases is just as perfect as the rotating field you make from three phases, because from both of them you can make a vector which rotates continuously. Okay? So in terms of the rotating field created, the quality of the rotating field created, there is no difference between two-phase and three-phase. But still, all of industry is using three-phase. A lot of control motors are two-phase. As I mentioned before, stepper motors are actually rotating field motors with two phases, which we'll discuss later on today. So why is it that all industrial motors are three-phase and all the small motors, not all, but many of the small motors are two-phase? So we went through it in great length. So why?
Three-phase are more efficient.
Why? Why is it more efficient?
Because for the number of inductors and the force you get out.
Very close, yeah. So basically, because three-phase sums back to zero, you save some copper. Because I gave the rough calculation. If you have two phases, you still need three wires, okay? And if you have three phases, you have three wires. But if you do the calculation, and I just did a very rough calculation with you last week, but basically, if you do the calculation, if you want to do the formal calculation, you have to calculate the currents to generate the same vector. Say if this is a unity vector, okay, so you have to compare apples to apples. You have to calculate two-phase, say you call the currents in the two coils. Say this will be I and this will be I, and the current I, let's say, generates a unity vector, okay? So in other words, the vector is I sine theta plus I cosine theta, okay? So if you have these two coils, you get I, but you need a return current. So if this is I, this is I, this, the common wire, these are the two coils. The common wire will carry sine theta plus cosine theta, and I mentioned that sine theta plus cosine theta is some waveform where the minimum is 1 and the maximum is 1.4, square root of 2. So let's call it 1.2, okay? So to generate a unity vector, you have to carry three conductors, one carrying I, the second carrying I, and the third one carrying 1.2 I, roughly, because it's a sum of sine and cosine. I made it very rough because you have to take the RMS, of course, and so on, but it's about that. Now you have to think about what do you do in three phases. So in three phases, I just showed it very crudely as you carry 3 times I, and you generate three fields. If you want to be a bit more formal about it, then you have to actually calculate what do you need for a unity vector. So in three phases is sine theta. This is sine theta plus 120 degrees. This is sine theta plus 240 degrees. Okay? So this is, so both in space the coils are 120 degrees apart, but also in time the signals is the same as here. In space the coils are 90 degrees apart, but also in time the signals are 90 degrees apart. So here, say if this is 0, if sine theta is 0, this will be sine 120, which is like sine 6, will be 0.86 roughly, and this will be sine 240, which is minus 0.86, so the two vectors will be like this. Okay? So if you draw the two vectors, it will be like this, where this angle is 60 degrees, so you can generate the combined vector, but the combined vector is bigger than 1, so you have to scale the currents to 1 and add the 3 currents, and this will be how much copper you need. So if you want to do it more formally, okay, we can do it. So this is so because sine 240 is minus 0.86, the vector is actually pointing this way. So this will be 0.86. This is simply square root of 3 over 2, right? Because sine 120. Okay, and this is roughly 0.86. So it's like this. So you can calculate how much does it work out to be. So this is 30 degrees. So this will be 0.86 of 0.86, right? So 0.7. This will be about 1.4. I mean, I didn't do the calculation. So now actually the current to generate a vector of 1 is actually less than I, right? If the coils were the same, so the current is actually less than I, and you have to take 3 of those currents together. So let's say this current will be is about 0.7, so it will be a total very, very roughly of 2.1 I. Okay, so again, it's a very informal, it's still informal calculation, but you can see that the amount of copper you need for the same I squared R loss, because what you want to minimize is the I squared R loss in the transmission lines which bring the power. Okay, so say for the same I squared R loss, since you have I, and I 1.2 I, you have to handle a total cross section of copper to handle about 3.2 I. Okay? Because you can treat all the conductors as carrying one big current, which is a sum. That's clear? So here, to create the same unity vector, if you go through the calculation more carefully, you have to have a total amount of copper to carry about 2.1 I, very crudely. So this is much more efficient to generate the same unity length rotating vector. Okay? This needs about, whatever, 2/3 of the copper. Okay? It's not so important to do the exact calculation. It's important to understand the principle. So is it clear to everybody why in the transmission lines you need less copper if you're driving a 3-phase motor than a 2-phase motor? Is that clear to everybody? Good. Okay, so why is that the small motors, like stepper motors, little servo motors, why are they 2-phase? The answer is simple, because when you build a little instrument, you don't have the long transmission lines, right? When you build a little control or robot, what's more important is to make the motor simpler and lower cost. Because a 3-phase motor has 3 sets of coils, so a 2-phase motor is a little bit simpler. It has 2 phases, 2 sets of coils. So because the motor is a little bit cheaper, a bit simpler to drive, if you're dealing with small motors, the saving of copper on the long transmission lines is not important. It's more important to make the motor a bit simpler. So because of this, the little rotating field motors, like stepper motors, are always, or almost always, 2-phase. Same is true for a type of motor called, there's a special type of servo motor which runs on AC, called control motor. All these are 2-phase, and the big industrial motors are all 3-phase. When Tesla came up with that story, he started with 2-phase, and then he realized that 3-phase would be better for transmission lines, and he switched to 3-phase. And after that he was obsessed with the number 3 the rest of his life. I mentioned to you that the reason we have 60 Hertz in North America and 50 Hertz in Europe, because Tesla had the patents on the AC system, and he believed a man should never work with numbers which don't divide by 3, so he didn't allow Westinghouse to use 50 Hertz in North America. They fought bitterly over it, but he refused to give the patents unless it's divisible by 3, and that's how we have 60 Hertz. Okay? Good. By the way, that's the history of most standards in the world. If you go back and read the history of most standards in the world, they have some insane, completely insane story behind them. How they became a standard. I'm serious, like the typewriter layout, and you know the stories. That's common stories. Okay. Is that all clear? Okay, now let's move on. And so all this was a recap of last week. So let's move on and talk about what happens if you have more than one set of windings. So what I described is I described a motor which had 3 coils, to make it very simple. And the 3 coils generate a rotating field, and if I put a magnet inside, that magnet just follows the rotating field. Okay? What happens if I take a motor and I put in another set of 3 coils? So then I'll call the 3 phases RST, which is a normal convention to call the 3 phases. So RST are the 3 phases. They are basically 3 sine waves, but just shifted in time. Okay, so whatever. Like this, 3 sine waves shifted in time. So what happens if I add a second set of 3 coils? Okay, and I connect the 3 coils, and I connect them in a way that, let's say, if this was R, I make this S, okay, and I make this T, and then I start again, R S T, and then I start again, make this R, make this S, and make this T. Hold on. RST. Oh, okay, that's why. Okay. So I have one set, I have one pair of 2 coils, one pair of 2 coils, one pair of 2. Sorry. Okay, so it's just drawn badly. Okay, so I connect them. Put another set of coils and put R, S, T, and then I start again. R, S, T. So now I have 2 sets of 3 coils, and I connect them with the same 3 phases. And so what will happen here? Because the peak of the magnetic field will switch from R, S, T, okay? And then again the peak will be here, R, but a new peak will come out here. Okay? So let's say the simplest way to think of it, if this is following the peak, let's say the peak of the magnetic field is north, and this is trying to follow the north. Okay, so first the peak is here, the north, so the north will, let's say south, will point here. Okay, let's call it south. So the north will be follow the south. Now, a bit later, 1/6 of a cycle later, the peak of the south will be here, so this will be here. And then the peak of the south will be here, this will be here. But then the peak of the south will again appear here and here. Now since this is already closer to this one, it's not going to go back all the way, it's going to keep following this way. Okay? So another way, if you don't visualize it, imagine it a different way. These are the 6 coils. Imagine you put a little ball here, a metal ball. And this is the peak of the magnetic field. Now the peak moves to here, now the peak moves to here. So the ball is now here. Now then the peak moves back to here and here. But the ball is already here, it's going to be pulled to here. So what happens? You will get a rotating field, but the rotating field will rotate at half the original frequency. Because originally if the peak went from here to here to here, in one sine wave, you got a full rotating field. So in one sine wave, the armature made a full rotation. But if you have 2 sets of coils, it will go, peak will go from here to here to here, and at the same time, there will be another peak which will go from here to here to here. Okay? So if you had a little metal ball or a magnet, it will go half a rotation and then continue. So it will take 2 sine waves to make a full rotation. Is that clear to everybody? Of course, if you want to optimize such a motor, what you do, you don't have a bar like that, because at any point you actually have two peaks. So in order to optimize such a motor, you actually make an armature which looks like this. So this is NS, NS, because this way you take advantage of the fact that you have two peaks and you pull those and those. Okay, which makes sense because this motor will go at half speed, but because it has duplicate coils, you can double its torque by putting two magnets, and since the power is torque times omega, it will end up the same power. Because if you have two sets of coils, omega will be half, but torque will double, because you can do this kind of armature which takes advantage of both peaks. Is that clear? Okay, so a set of coils like this, a set of coils which generates an N and an S, is called a pole pair. Okay? Now, and if you have a motor which has one pole pair and it has a rotating field like this, you drive it with 60 Hertz. How many RPM will it have?
30.
RPM. How much?
1800?
Okay, one pole pair. So I'm talking about a motor which is, I'm talking about the original motor. It has one set of coils. Okay, so this will be, so in one cycle, the vector will make one rotation. And we connect it to 60 Hertz power line. So how many RPM will the motor will have? 3600, because in 1 minute there are 3600 cycles. Each cycle the magnetic field will make one rotation.
So that's one pole pair? Or that's
Oh, okay. So this is a very confusing term, because this thing is called one pole pair, not two poles, because there is it's a very confusing terminology, because sometimes you see in books it says a two-pole motor or a four-pole motor. What they mean is two pole pairs or four pole pairs. Okay, so the terminology is very confusing, because magnetic poles always show up in pairs. You cannot have an N or just an S. Okay, so most of these motors physically are wound. If you want a motor, like a DC motor, to have one magnet, you wind it already with two coils. This is N, this is S. So when you look at it, it looks like there are two poles, but it's actually one pole pair, because you cannot have only one pole. Okay? So the terminology people use is pole pairs, but in some books it just says poles, but it's the same as pole pairs. It's a very confusing terminology, and sometimes you have to make sure that the author meant what you meant. But the most common terminology is to count pole pairs. So this will count as one pole pair, and if this was a three-phase motor, so there will be a coil like this, a coil like this, a coil like this, but they will create one pair of NS poles which rotates. Okay, in other words, there will be one vector which is like NS, and this vector will rotate, so at the end there are three coils, but they generate one rotating magnet, so it's one pole pair. So this will rotate 3600 RPM. So this example I gave here, where you add a second set of coils, here I added a second set of coils, so there are actually two vectors which rotate, right? Because one vector is rotating like this, but at the same time there's another vector, because I have two sets of coils. Each set of coil generates a rotating vector. Okay? So this is called two-pole pairs, although when you look at it, you're saying, I see 6 coils. But it doesn't matter, okay? What matters magnetically, how many rotating vectors simultaneously there exist. Okay? So I know it's confusing. In a DC motor it's simpler, because in a DC motor it's always a fixed coil N and S, there is no rotating field, so you just see how many of those sets there are, and each set is a pole pair. Yes?
So
It's the same wire. This R, and this R are connected together to the same wire.
So how do they not cancel each other out?
Okay, what happens is they don't cancel each other out because each one generates a rotating field. Like here you have a field where the peak goes from this to this to this and back from this to this to this. Here you get a field where the peak goes from here to here to here. So they don't cancel themselves out because what happens now, and I'll draw the field here. If you had the original motor like this, the field went like this across the whole motor. So you had one vector which rotated. Now if you double the number of poles, okay, let's say we draw 6, and you wire it the way I showed, the field will actually go like this, because this is RST, and this field will go like this, and now the whole thing will rotate. Okay? So there's actually be two sets of fields, and that's why you make the armature like this. So two of the magnets lock to this field, and the other two magnets lock to the other field, and you get double the torque. Okay? So I realize it's confusing. You know, you can think about it a few minutes, it'll become clear, but what's important to understand is that what you count is how many simultaneous sets of poles you have. Or if you want to think a different way, at how many places does a magnetic field peak at the same time? Okay, so here the magnetic field peaks at one point, and this point rotates if there are 3 coils. If there are 6 coils, the magnetic field peaks simultaneously at 2 times, 2 places, and both rotate. So it's the same as having 2 bar magnets rotating. So this is called 2 pole pairs. Okay? So if you look at the structure of the motor, by the way, if you open a motor, it's not obvious at all how many pole pairs it has, because I mentioned last week that physically, even if a motor has 1 pole pair, a 3-phase motor, when you open it, doesn't really have just 3 coils. It has many coils to distribute, to make the field more uniform, and these coils are grouped as 3 poles. So when you actually take apart any kind of 3-phase motor and you look inside, it looks like this. It has maybe a dozen coils. So inside of a 3-phase motor you have 1 coil here, 1 coil here, 1 coil here, 1 coil here. So when you look at it, you see dozens of slots, and you can't see is this 2 pole pair or 1 pole pair, or 3 or 4, whatever. Okay, because you can only see if you look at the wiring diagram how they are grouped. Okay, so it is slightly confusing, but it's not so important. What's important is just the principle. Yes?
What is the relative position of the rotating vectors for the 2-pole pair?
Okay, so in the 2-pole pair, depending how you lay out the coils, okay, you can lay them out different ways, but the simplest way to think of it is if I'll draw just the magnetic poles. These are 3 and these are the other 3. So this will be like, at any given moment, this will be like N, this will be S, and this will be somewhere in between, let's say 0, and then it will keep rotating. And here again it will be N, it will be like something around 0, and this will be S. Okay, so the magnetic field which wants to go from N to S is going to go like this. Okay, but as this changes, as this becomes N, and this becomes 0, and this becomes S, then this magnetic field which I drew will now rotate. So this is, say, at t equals 0. Now if you draw the same thing at t equals 1, this will become N, so the magnetic field will look like this, and like this. Let's draw it in a dotted line. Okay? And again, a third of a cycle later, the magnetic field will go like this. But because the magnetic field doesn't go across, but now goes across only half, then you are gaining by making an armature which has ns, ns. So this captures this part and this captures this part. Okay? You can lay it out different ways too, but that's kind of the simplest way to understand. Again, if you open such a motor, it wouldn't look like this at all. If you open such a motor, it will have a dozen coils distributed in two groups. Okay. Good. So if you had a two-pole pair motor like this, you hook it up to 60 Hertz, what RPM will it have? 1800. So a two-pole pair is 1800, and a three-pole pair, you get the idea. It's 3600, which is a synchronous speed, divided by number of pole pairs. Okay? So say if you look at your furnace, if you have a furnace at home, you look at the motor, it says on it, it actually should be 1800, it says on it 1750, but I'll explain this next week because that's actually, or Thursday, because the motor you have at home in the furnace is actually not a true synchronous motor. It's what's called an induction motor. So it runs a bit slower, but we'll get to that. So I'm thinking of an example. In a home you don't really have truly synchronous motors except in your disk drive and your electric clocks. So you really can't think of an example at home. But basically for a given synchronous speed, which is 3600, which is a line frequency, okay, every pole pair you add divides it. So one pole pair is 36, 2 is 18, and so on. So typically you don't make motors with hundreds of pole pairs because it will require too many windings. So if you want a motor to go very slow, you don't put 100 pole pairs, you just gear it down. So if you want something to go slow, you either pick 1800 or maybe 900. Beyond that, you just gear it down. Okay. So the second thing I want to discuss is what do you do in a house, like in a normal residence, which doesn't have three phases, and you want to use rotating field motors. So we are going to cover the most popular type of motor. It's actually called an induction motor, and we'll cover it Thursday. But even before we cover it, I want to cover the ways to generate a rotating field out of one phase. Because at home you only have one phase, and both for induction motors and for electric clocks and for many other reasons, you want to generate a rotating field. So does somebody know how do you make a rotating field at home in the motors, like in your furnace motor, washing machine motor? How do they generate a rotating field? Because obviously these motors, when you look at them, don't have brushes, and they are not brushless DC. They are rotating field motors. Okay, the constant speed. You can see the rotating field motors of a type we'll discuss Thursday, but how do they get the rotating field? Any ideas? So remember, the minimum you need to get a rotating field is two phases, where one is I times sine omega t or theta, and the other one is I times cosine omega t. So you need a neutral, or say common, in two wires where the currents are 90 degrees phase shifted. That's all what you need to generate a rotating field. So any ideas how they do it at home? You must have taken apart once some table saw or something to. Okay, I'll give you a hint. When you look at your table saw motor or washing machine motor, the motor doesn't look like a normal motor in the pictures. It usually has a hump here. Okay, all these motors at home have a hump on them, like a camel. What's inside that hump? Nobody ever took the cover off a motor? Yes? Capacitor, very good. And why is there a capacitor inside that hump?
Provide a phase shift.
Ah, because you know or should know that when you have, when you have a current, if you put a resistor, the current in the resistor is in phase with the main current, okay? But if you put a capacitor here, there is a phase shift. The current here is phase shifted, okay? So, or voltage, doesn't matter, we talk about voltage or a current. So if you have a voltage, this will be lagging, this will be later, okay? So say if I do this, okay, this is ground, I put a voltage here and I check the currents. Okay, this current will be in phase with that. So if this is sine omega t, this will also be sine omega t because the resistor doesn't shift the phase. Okay? But if I put a scope here, I see a sine wave which is phase shifted. Under ideal conditions, it will be phase shifted 90 degrees. Okay? And can somebody explain why under ideal conditions this current will be shifted 90 degrees compared to this current? So what is the proof or formula? Why is that 90 degrees? Why not 17 degrees? Yes? Indirectly, but there's a simpler way to prove it. What is the current in a capacitor? If you have a changing voltage on a capacitor, what is the current? I mentioned it several times in the course. Ah, very good. Current in a capacitor is C dV to dt, and if V is sine omega, dV to dt is cosine. It's as simple as that. Okay? Because this current is the derivative of the voltage, not the voltage. So because of this, if this is sine, this will be cosine, and if you put a coil here, say if you put one coil here of the motor and another coil here, you get two currents in quadrature and you have a rotating field. Okay? So physically, the way this works inside, physically, say you have one coil like this and one coil like this in quadrature. Let's say the coils are connected together to neutral, and now one coil is connected to the line and the other coil is connected to the line through a capacitor. Okay? So this is sine, this is cosine, you get a rotating field. So you can run a motor from a single phase because it generates, a capacitor generates the other phase. Yes?
What do you mean when you say in quadrature?
Quadrature means 90 degrees. When you say in electrical engineering quadrature, it means 90 degrees phase shift. That's what the term quadrature means. So, okay, so here, because the current is a cosine, if the voltage is a sine, and the coils respond to the current, this current and this current will all be in phase. But you have to be a bit careful, because here, if you choose the wrong value capacitor, you wouldn't get 90 degrees. The reason is the coil changes the equation, right? Because the current here is actually V divided by Z. So the real current here is actually V divided by Z, not V divided by J omega C. So you have to be careful that the capacitor will dominate, right? But for an approximation, it's good enough. If the capacitor dominates, in other words, if this delta V is small compared to this, the capacitor will dominate, the current will be the derivative, we'll get quadrature, we'll get two currents roughly at 90 degrees. If there was no inductance here, it would be exactly 90 degrees, okay? Because of the formula. But because the inductance modifies the equation, it will be, say, 80, 70 degrees, but good enough to generate maybe not a perfect rotating field, but something which is close enough. Okay? So let me demonstrate to you. So I have a motor here with a marker. So first, see, okay, let's see. Okay, so first let me turn it on, and this is turned on just on one phase without a capacitor. Okay, so it just vibrates. You cannot see it vibrate, but I can feel it vibrate. Now if I take the same motor and I connect the capacitor to the other coil, so let me turn it off again. Just put it down a place you can see it. Okay, now I'll turn. Have to be a bit careful because it's line voltage. It's running straight on the line voltage. Okay, so this is this. This is this. Okay, we'll. I'll explain this on Thursday, but right now we're just dealing with two phases. Okay, so I'm running it on one phase. Right now only one coil is energized by one phase. It's just humming, but not rotating. Now I have a capacitor here. If I connect the capacitor to the other phase, I generate a rotating field, it starts spinning. Okay? The mystery I'll explain on Thursday. Why does it keep spinning after I disconnect the capacitor? Okay? Anybody who explains this can get an A without doing the final exam. Okay, but anyway, but what happens here, that the main thing I wanted to show you is that with one phase I could just the motor just vibrated. With two phases, even if the other one was artificially made with a capacitor, it rotated very nicely. Okay? Now, I mentioned before that stepper motors, like the ones you are very familiar with, are actually exactly the same construction as synchronous motors, but they have many pole pairs. Okay? To prove it, I'll first show it to you, then I'll explain what's inside a stepper motor. So to prove it, a stepper motor has two coils. Okay? 4 wires come out of it. So what I'll do is I'll take and energize first one coil of the stepper. Okay, so I give it some voltage. So if I energize one coil, you can see. If I energize one coil, it just vibrates. It can't rotate. But if I take this big capacitor, okay, and I add it to the second coil, okay, so this should go here, the motor starts rotating now. Okay, if I remove the capacitor, it goes back to vibrating. So basically the capacitor generates a second phase which I needed to make a rotating field. Okay? Now to see if you really followed. It turns out if you open up a stepper motor, it has 50 poles, 50 pole pairs. So all stepper motors that you are using, the standard ones, which are 200 steps per revolution, the standard stepper, inside if you open it up, if you count, you see on the armature there are 50 slots, 50 pole pairs. Okay, so at what speed, at what RPM did it rotate now when I give this demo? How much?
720.
Say it again?
720.
It didn't look like 720. It looked a bit slow, right? So, watch it. You saw it. It went quite slow. How much?
72 RPM.
Ah, excellent. Okay, good. Okay, but that's the right idea. Anyway, so, very simple. If synchronous speed is 3600 and the stepper motor, I'll show you in a minute why, has 50 pole pairs, okay, you get 72 RPM. Good. Okay, so what's inside the stepper motor? So I already explained that it has 50 pole pairs, so it has an armature which is a permanent magnet which looks like this, which has 50 pairs of NS, NS, NS. By the way, the way you make 50 pairs, it doesn't mean you need 50 magnets, right? Because you can make 50 pairs from one magnet. because all what you have to do is you have some gear. All what you have to do is you say, if you take a magnet, okay, and the magnet has just a single pair NS, and you make a blade of metal, which has 50 T's, and you make another blade which has 50 T's, and you put this blade here, you get 50 N's, and here you get 50 S, and now you can bend them to interleave, then you get 50 pole pairs. Right? So 50 pole pairs, I'm just trying to explain practically, 50 pole pairs doesn't mean 50 magnets. It just means you lay out the metal to make the magnetic flux flow to get 50 pairs. Is that clear? So again, if we say if the chalk was a magnet and I put it between my fingers, so I have on this side 5 N's, on this side 5 S. Okay? If I do this, if I interleave, I have NS, NS, I have 5 pole pairs for one magnet. Good. Okay. So, why is it that this is called a 200 pulse per revolution? When you look at this stepper, it's in the catalogs, it's referred to either as a 1.8 degree per step. Okay? That's kind of the most common stepper used, 1.8 degree per step. And if you take 360 degrees divide by 1.8 degree, you get 200 pulses per revolution, PPR. Okay? I mean, all of you use this kind of stepper, I'm sure, so that's the most common stepper on earth. So, can somebody explain, if it has 50 pole pairs, how is that related to pulses per revolution? But think of it, a stepper is usually not fed with sine waves, it's fed with square waves. Unless it's microstepped, which we'll cover next week, or maybe cover a bit today. But if you think of it, if you replace the sine waves with square waves, how many pulses will you need to get a full revolution on this stepper? So you know it's 50 pole pairs, right? So can somebody explain why is it 200 pulses per revolution? Pardon?
100 poles and then there's 2.
But there's only 50 pole pairs. Remember, the magnetic field only comes in pairs, so it's actually 50, not 100. Because what matters is pole pairs. For every N there is an S, so they're not independent poles. Okay. Okay, so let me lead you through it step by step. First we'll draw the two sine waves. We know that a stepper motor, if we run it like I ran it here, if we run it like a rotating field motor, is run by a sine and a cosine. So one phase begets sine omega t, and the other phase will get a cosine. So we'll draw it nicely like this. Now we have to draw it nicely because I need the exact timing here. Okay, so this is one cycle. Okay. Now, if I replace this with square waves, because the stepper, when I run the stepper on pulses, it's running by square waves. So what I do is I replace the sine wave by a square wave. So one phase will get this, and the other phase will get this. Okay? So if I feed the stepper with two square waves like this, which continue, each time I give it these two square waves, it will move 1/50th of a rotation. Because we said that if you have n pole pairs, the synchronous speed will be 3600 or will be basically whatever the frequency is divided by n. Right? Like if it was 50 pole pair on 60 hertz, it will be 60 hertz divided by 50 pole pairs. So, if I take the stepper motor and I give it one cycle, it will rotate 1/50th of a rotation. Because just like we went through with the other motors before. Okay, but a 50th of a rotation is not 1.8 degree, right? 50th of a rotation is 4 times as much. Okay. Right? So where is it? What's the catch? Okay. So we all agree if I give this to a stepper motor, it will rotate 360 degrees, divide by 50 because it has 50 pole pairs. Okay. So it will rotate 7.2 degrees. So why do we call it? Why do you say 200 pulses per revolution? Yes.
Because we're sending pulses that are basically on-off, and you have for each wave you have a 2 on-off.
Very good, very good. Because when we count pulses, we're actually counting transitions. Because the way we drive a stepper motor, we have a clock. Now the clock generates the transitions. Each time the clock pulses, there is a transition. So this is actually 4 transitions. If I count the transitions, I have a transition here, which means a clock pulse. Then I have a transition here, which means another clock pulse. Then I have a transition here, which is a 3rd clock pulse. Then I have a transition here, which is a 4th clock pulse. So this is the clock, and now it starts again. So to generate a sine wave and a cosine wave, it takes 4 transitions. And when you make a stepper motor driver, what you're really counting is transitions, because the way you do that, you have some shift register driven by a clock, and this takes 4 clock pulses to generate these 2 waveforms. So this term 200 pulses per revolution is misleading. It is not 200 pulses, it's 200 transitions. Okay, it's actually only 2 pulses, okay, but each pulse is 2 transitions. Okay, is that clear to everybody? Because that's very important. That's basically the fundamental difference between a not the difference, but the fundamental principle of a stepper motor. Okay. Now, before I move on a bit further with stepper motors, can somebody think of another way to generate a sine and a cosine from a single phase? Because I said the common way is a capacitor, and we explained and I showed it to you, but it turns out there is another way. You can generate a sine and a cosine from a single phase, and if you can generate a sine and a cosine, you can generate a rotating field. So I also want to point out the other way, because in case you run into it, it's actually an interesting idea. So can somebody think of another trick very similar to the capacitor trick, which simple laws of nature force the current to be at 90 degrees phase shift? Yeah.
An inductor in series?
Pardon?
An inductor in series?
Okay, so if you just put an inductor in series, it doesn't work that well, although it works somewhat, because the coils are already inductors. So let's say if you have the 2 coils of the motors, okay, which are physically in quadrature. Inside the motor, the coils are at 90 degrees. Now, if you connect one direct and one with an inductor, okay, and this goes to ground, and this is V, there's not going to be a huge difference because both are inductors. Now, the reason there will be a slight phase shift, because this inductor is not ideal, it has some resistance. So the only reason why there will be a slight phase shift is, you recall from before, the vector of the current in an inductor, if there is some IR drop, and there is j omega L times I, the vector is actually a little bit off from 90 degrees, because there is a IR component. But it's not a big difference because both are inductors. So if you just put an inductor in series, it may be enough, but the motor will have very low torque. because the phase shift between the two is going to be very small. So we need another trick. Okay, I'll give you a hint. When you look inside one of the few synchronous motors you have at home, which are electric clocks and timers, if you ever looked inside a timer, that's an industrial timer, but at home you have the same thing. Okay, so if you look inside the timer, you see some copper pieces mounted on the motor. What you see is a motor which rotates from a single phase, but you see some copper pieces mounted on it. Okay, did anybody think what are these copper pieces for? Okay, so while I'm talking, I'll pass it along. I want everybody to look at these copper pieces, and also there is a solenoid, there is an electromagnet here, and I want everybody to look at that electromagnet as well, because it has a similar copper piece. Okay? So, and then while you look at it, I'll explain it. So look both at the magnet and the motor. Okay, so I'll tell you the solution and I'll let you explain it. So the other way to achieve a rotating field, or to achieve a sine and a cosine given a single sign, is you take the magnetic pole. Now this is the magnetic pole, and this is other magnetic pole. Okay, the motor, and what you do is you make a slot in the magnetic pole. Okay, and this is a coil. This is a coil here, and this is a coil here. You make a slot in the magnetic pole, and you put a short-circuiting coil, which is basically a copper ring. You put a copper ring, which is a short circuit around half of the pole, or fraction of the pole, and you do the same here. You put a copper ring, and when you pass along this motor, you'll see that's exactly what it has. It has a copper ring around part of the pole. Okay, so that is a solution. Now, can somebody explain it? Why does this generate two phases? Yes.
Is there AC current going in?
AC current, yeah. We're all talking about ACs. These are all AC motors. Yes?
Does it have something to do with induced currents that then produce the magnetic field to oppose the original one?
Very good. Ah, excellent. Okay. So remember Lenz's law. Lenz's law says that any induced current will try to cancel the current which created it. Okay? So what happens? That the magnetic field is trying to come out through both sides. On one side, it's coming out straight. On the other side, it induces a current which opposes it. Okay? But the current it induces is actually a derivative of the original current, because the same as in a capacitor, the current was a derivative of the voltage. If you have an inductor or a coil, the voltage is a derivative of, okay, so the voltage is a derivative of the flux. So the voltage is N d phi to dt. So if the flux was originally sinusoidal, if the flux was cosine, the flux was proportional to I, let's say sine, I sine omega t, because we are driving the sine wave through it. So the original flux phi, I'll draw it like this, phi was proportional to the sine wave. The induced voltage here will be proportional to the derivative. Okay? Now the induced voltage will induce a current which will create its own magnetic field, which will try to fight the original magnetic field. But the induced current will be at quadrature, will be at 90 degrees. So what you'll get here is actually a sum of the original field plus a field which is trying to oppose it. So another way of looking at it without the mass, which may be simpler, if the flux originally was a sine wave, assuming the phi originally at this point was a sine wave. So at the points where the phi is not changing much, there will be very little induced current, very little induced flux by the secondary coil. Because the only time you get an induced voltage here, and this changes a lot. Okay? So if this was the original flux, the biggest changes are here, because the slope of a sine wave is biggest here. Okay? So here, here, and here, there will be a big induced current and induced flux. Here and here, there will be minimal induced current, induced flux. So the flux the secondary coil induces is actually a derivative of this. It is big here and little here. It looks like this in a dotted line. Okay? Because one is simply the derivative of the other. Now in some complicated way you get a sum of these fluxes, so you don't get exactly 90 degrees, and depending which is bigger and so on, but you get some phase shifted flux which is phase shifted compared to this flux. Okay? So now, in order to get a rotating field, you don't really need 90 degrees, you just need two vectors which are not collinear. Because when we derived the rotating field, we had two vectors. One was sine, one was cosine. But if this other vector was smaller, or was maybe not at 90 degrees, what will happen? The superposition will not give you a rotating field, it will give you some elliptical field. But that's good enough. So, bottom line is, if you don't need much torque, if you just need a rotating field, and the motor doesn't have to be efficient, you actually don't even need a capacitor, you just need to phase shift part of the flux. And once you phase shifted part of the flux, you generate a small vector which is out of phase with the main vector. That's all what you need to have a rotating field. Okay? So this kind of motor is called shaded pole motor. It's not very important because it's not used that much, but just in case you see it in a motor, you know what it is. Where it is used more is actually in actuators or solenoids which have to work in AC. So in the motor I'm passing here, when you look at it, next to the motor there is also an electromagnet. So next to the motor there is an electromagnet. And this electromagnet, which has an armature, just like the classic actuator, and has a coil, you will see it has the same trick here. It has a slot here, and there is a copper ring shorting part of the flux. Can somebody explain what's the purpose of this copper ring? Because obviously here we don't need a rotating field, right? Because the field is just going like this, attracting the armature. So what's the purpose of the same trick in this electromagnet which is attached to the motor I'm just passing? Yes?
To help it operate more linear.
Why would it be more linear?
Because the magnetic field increases, or force increases, it gets closer to reduce the knob.
Not quite. When it gets closer, it becomes more linear in AC because of something else we talked about before. The inductance goes up, current goes down. But just adding the copper ring will not affect that. But let's see if there's other ideas. Yes?
There's no zero crossing the intensity of the magnetic field.
Ah, beautiful. Because the problem with electromagnets operated on AC is that 120 times a second the flux crosses through zero. So each time the flux crosses through zero, the electromagnet wants to let go. But it doesn't have a chance to let go. It just lets go a little bit and the flux pulls it back. So all AC electromagnets make a big noise. And last time I had a solenoid here when we talk about snap. And as you recall, you could hear the very loud noise when we ran it on AC. Just before it snapped, it made huge noises. Because the flux goes through zero. But if you have two fluxes and they're out of phase, the sum never crosses zero. Right? And that's good. Because think of it, if you have a main flux and then you have a little flux, which doesn't have to be even the same, okay, and you add them together, you can end up with something which never crosses zero. Because all that you have to do is you have to add a little flux which is out of phase with the main flux, so it'll fill up the zeros. Remember, the pool is a rectification of the flux. If the flux is this way, the pool is this way. Okay? Because whether the current goes one way or the other way, in both cases it pulls. Because that's not a permanent magnet, it's just a piece of iron. So you get 120 times a second where the pull is zero. But if you have a little flux here out of phase, then it generates another pull which goes through zero here. But when you add them together, you ended up with something like this, which never goes through zero. So all AC relays, AC electromagnets, they all have this trick. Okay? So when it comes back here, when I have time, I can connect it to AC to show you it closes with no noise. Okay, so we talked about, so this was just an example that there is other ways to generate a phase shift, but 90% or 99% of motors which run on one phase and make a rotating field use a capacitor to make the rotating field. So if you look at home, your furnace, your table saw, it's always a big capacitor on it. Okay, so now, so the last thing we have to talk about is microstepping. So, okay, so what happens if we take the stepper motor and instead of running it with pulses, like it's run many times, we'll actually run it with sine waves. So let's say we take the stepper motor, we'll run it with a sine wave and a cosine wave, but we have the ability to freeze that sine wave in time. Because when the sine wave is coming from the line frequency, we cannot stop it. But if we generate this electronically, we can freeze it. Let's say we freeze it at a moment, and then we continue. We continue, and this continues up like this, and then we freeze it again. So what will happen to the motor if we ran it with a sine wave, and from time to time we just stopped the sine wave, froze it, and then continued? What will the motor do? Well, I can even do it with this one. I can just disconnect it. I can run it like I ran it before, and from time to time, but disconnecting it is not the same as freezing the sine wave. Because when I disconnect the stepper motor, it will tend to pull itself to the nearest natural detent of the magnetic field, and I'll explain in a moment what that is. But let's continue with this line of thought. What happens if I run it with a sine wave and from time to time freeze the sine wave in time? Okay, what happens is, think of it, these two sine waves generate a rotating vector, which you already know. So the rotating vector is rotating slowly with the sine wave and dragging the armature with it. Now the moment the sine wave freezes in time, the armature freezes in space. It's the same position it was. Because inside that stepper motor, there is a rotating field which is dragging with it a magnet. Never mind that there are 50 of those, but in principle there is a rotating field dragging a magnet. This rotating field makes a rotation for each sine wave. Now because there are 50 groups, it's actually 1/50th of a rotation on the shaft. Okay? But the moment I freeze a sine wave is I just freeze the rotating field in space. If I continue, it continues rotating. Okay? Now I can say what I can do is I can synthesize the sine wave. The way I synthesize a sine wave is I take a lookup table. So I have you know what a lookup table is, right? So I take in memory all the values of a sine wave and I output the values one by one. So it will look like this. It will have little steps, but in effect it's a sine wave, just made from little steps, just like in this variable frequency drive I had. So I can go through the steps which represent a sine table and a cosine table. The rotating field will rotate beautifully. If I stop the advancement, it will freeze. If I start clocking the table again, it will continue, the sine wave continue rotating. Okay? So this is called microstepping. And this is the most common way today of controlling a stepper motor. Now the reason why it wasn't popular in the past, because you need electronics to do that. In the past electronics was expensive, so people looked for tricks how to make the stepper motor rotate and stop without resorting to that. But today this is done with actually PWM. So when I want to generate a sine wave, like this, which is made of steps, I don't actually have an analog amplifier which generates these steps. All what I really have to do is change the pulse density. I start off with some narrow pulses and then I change the pulse width. Okay? So this way, by using PWM, I'm generating the average value which represents a sine wave. So when you think of it, in order to take a stepper motor and make it rotate to any position and hold the position, all what you need is two wires carrying a pulse train. Now, the average value of this pulse train on one wire has to represent sine theta, and the average value has to represent cosine theta. And I can freeze it. At any moment I can freeze it to a certain voltage, and a certain voltage means a certain duty cycle. So when I say freeze it, I mean keep the duty cycle constant. So the moment I freeze the duty cycle, it's the same as freezing the average value. So the moment I freeze the duty cycle, the average value is frozen and the stepper motor holds position. Okay? And then if I let the lookup table keep counting, the duty cycle changes. So what you really see when you put a scope, you see just this. But what this represents is a sine wave and a cosine wave, okay, which are made from discrete steps, and you can control the armature very smoothly. A normal stepper, each pulse will jump 1.8 degrees. Here it's not going to jump at all, it's going to rotate smoothly. Just like in the stepper I showed you, when I connected it to the line voltage, it rotated smoothly, it didn't jump, because it was driven by a sine wave. So, is that clear to everybody? Yes?
What determines the microstepping number?
You determine it, because you program it. In most microsteppers, it's software selectable or switch selectable. So you can determine if you want to have, say, 100 steps per sine wave, or maybe you want even finer resolution, you can put 10,000 steps per sine wave. Like typical microsteppers, which are programmable chip or programmable module, they typically microsteppers allow you to choose from 200 to 25,000 steps or pulses, PPR. Okay. There's no point going below 200 because that's the natural resolution of the stepper. So you only go higher than that to increase the resolution. So that's kind of a typical range of microsteps. Now this is finer than you need because the stepper wouldn't even be able to hold position to that accuracy. I mean, you can divide it to 1,000,000 pulses, but it will be meaningless. So what I do want to explain again, and I'll repeat it Thursday, is there is a difference between freezing the microstep to a certain value and disconnecting the motor. Because when you disconnect the stepper motor, it tends to snap to the nearest position where the magnets lock in. Because if you think of a structure which has magnetic poles like N, S, and S, and then you have here poles of the stator. So when you take the power away, this will snap to the position where the flux is maximum. Okay? And there are 50 of such positions. So when you disconnect the stepper motor, it doesn't go to the nearest step. It goes to the nearest 1/50th of the rotation, which is 4 steps. Could be as big as 4 steps. Or maybe it'll go back 2 steps or forward 2 steps. But when you freeze the microstepping, even if the magnet is between 2 poles, it's not going to snap because there is some current in those coils which generate a resultant field which holds the magnet. So it's very important to understand the difference between disconnecting a stepper, and then it always will snap to 1 of 50 natural positions which minimize magnetic reluctance, okay? And between freezing a microstep, which can hold it anywhere you want because you generate a vector by the currents and the rotor aligns with that vector. That clear? Good. Okay, so we'll continue a little bit about microstepping on Thursday, and then we'll talk about other motors. Pass it very quickly so the rest of you can see it. Okay.